Well, good evening, everybody. Welcome to Space Oddities. If this is your first time here, you've made a big mistake. So anyway, not to worry. How is everybody out there? See, we've got some of the usual suspects in the chat already. Lovely to see you. Hope you've all had a great week. Welcome to Space Oddities. And it's been a funny old week here in Spain. We've had a combination of intense rain and record temperatures. So that's the way things are going, unfortunately. Anyway, enough of all that chutney. I'd like to welcome, as always, our resident Roger. He being Roger. How are you,
Yes,
Roger?
I am. I'm fine, thank you.
Good. And our resident Daz. How's Daz?
Oh, lovely, thank you. Lovely, thank you.
Well, that's a matter of
Bit
opinion.
cool
so
around the top of the head.
Welcome, Ian.
Hello, everyone.
Hello. Michael, how are you?
Hi there, I'm fine, thank you.
And Lou, how are you?
Surviving.
So what have we got for you this evening? Well, on tonight's show, Lou, before he has to rush off and teach, will be giving us the lowdown on dark matter, an introductory section on dark matter, which I'm sure Lou would be more than happy to delve more into it if that's what you would like at some point. But it's the beginner's guide to dark matter tonight, which we're looking forward to, because it's a puzzle, as you probably know, and it's one of the great unsolved mysteries of the universe. So we got that coming up. We've got, as ever, Roger's Guide to the Night Sky and the weekly Viewers Gallery. If you would like to send your images into the Viewers Gallery, then pop them in an email, one image per email, please, and address it to gallery@spaceoddities.space. Give us the details, description of the image, how you took it, what equipment you use, etc., etc. And there you are. And if you could please limit the resolution of your images to 1920 by 1080, that's HD. That would be much appreciated because it will save a lot of hassle. So there we are. Just a wee bit of housekeeping, as ever. If you would like to buy the Space Oddities merchandise, you can find it at the Space Oddities shop by scanning this code, which I'll leave up on the screen for a little while. We have t-shirts available at £25, including UK postage and packing. Hoodies available at £40, including UK postage and packing. And there you are. And if you're outside the UK, please add £10 to the total value of your order. So that's that. If you would like to support us, if you would like to donate some money to our coffee fund, you can do so by scanning this code, where you can buy us a coffee. Any coffee, gratefully appreciated. And as I always say, every bit of money received goes towards keeping the channel running and paying our bills. You can also click the super chat icon under the chat window there. It's the one with the $sign on it, to have your message in the chat illuminated. And you can donate whatever amount you like, no matter how big. We'll accept anything. So again, everything goes towards keeping us on the air. So there we are. So without further ado, I think we'll go straight over to Lou, as he has to go off and teach in about half an hour. So Lou, are you all set up there? Yes, you are.
We are set. Are
set. You ready, sir?
No, but we are set.
You're going to do it anyway, because you talked yourself into it. So
I did, yes. Well, so there are a number of great unsolved mysteries in the universe. Two of them that I think are at the top of the list is what is dark matter? How does it affect the universe? That's the first. And the other is why do they call them apartments when they're all stuck together? These are great mysteries that we need to solve. So addressing only the first one today, we're going to talk about dark matter. That you may have heard of this. I don't hear it much in the modern culture, in movies. We hear a lot about the multiverse and this kind of thing, but dark matter is a quandary. And the universe is not working the way we think it should. And so we're going to dive into this a little bit today for about 20 minutes. It could be a whole semester course, but no, we're going to do it in 20 minutes because we are most efficient here at Space Oddities. So let us move forward. This is the Coma cluster. It's a cluster of over 1,000 galaxies. It's about 100 megaparsecs away in the Coma Berenices cluster. A megaparsec is a million parsecs. A parsec is 3.26 light years. You do the math. It's a long way away. And in 1933, the Swiss-American astronomer Fritz Zwicky was observing this cluster. And he noticed that the cluster's mass needed to be much greater than the mass that he could account for in his observations. In other words, as a cluster, all of these galaxies are rotating around some center of mass. You might call it the Berry center. And they were just rotating too fast, given all of the mass that he could account for, which is the luminous material, the stars in the galaxies, the dust in the galaxies, in the infrared, the gas, all of that added up. And there's far too little to make these galaxies rotate, orbit this Berry center as fast as they are, given the stalwart equations from Isaac Newton that describe how all this is done, which have worked for us for 400 years. Actually, he had to give this a name because he didn't understand it. So he said, well, there's got to be a little more mass there. So he called it Dunkel Materie, which I guess is Swiss for dark matter. And that's kind of where it stood for just a little while. It's just a curiosity. Here we go. Then in the early turn of the century, there's an American astronomer, Vera Rubin, who was looking at individual galaxy rotation curves. So not clusters of galaxies, but individual galaxies and how fast they are rotating. And she uncovered a discrepancy between the predicted rotation rate and the observed angular motion of the galaxies by studying these galactic rotation curves. Those results were later confirmed by a number of other observations from other astronomers. And so again, if Isaac Newton's equations of force are correct, what is going on? It didn't make any sense. And here's why. Wait, did I go one too many? Yes, sorry. Here's a rotation curve for our solar system. The closer you are to the sun, the more strongly you feel the sun's gravity and the faster you orbit. Mercury orbits the quickest, not just because it has the shortest distance, but its velocity is the fastest. And as you move outward, Venus, Earth, Mars, and so on, you see this very nice curve of speed of orbit versus the distance of the planets. And this is exactly what Newton would predict. However, if you look at a typical rotation curve for a spiral galaxy, that is not how it behaves. It is essentially flat. If you go from the center of the galaxy outward, the speed of rotation is essentially flat as you move toward the edge of the galaxy. And it turns out that the way to make that happen, once again, is to add an awful lot of matter, in this case, almost 10 times as much matter as Vera Rubin could account for in her observations. And so here it is again. We're starting on the x-axis, it's distance from the center of the galaxy outward. From the x-axis, on the y-axis, it's the velocity of rotation. And we see two curves here. CDM stands for cold dark matter. And this is the missing matter that Zwicky hypothesized and that Vera Rubin thought must be there. This dark matter, this stuff that is not interacting electromagnetically or in any other way except gravitationally with its surroundings. So very, very weird kind of new matter, if you will. On the top here, the yellow dots and the blue dots, that is the actual data, the rotation curve data from observations of 21 centimeter neutral hydrogen in a spiral galaxy. So the dots are the data. The dotted curve is what you would expect to find from Isaac Newton. And if you add cold dark matter in the right proportions, in the right places around this galaxy, you can actually fit the observed data pretty well. Okay, so the CDM model says that there's a lot of extra mass, perhaps 10 times as much, in the spiral galaxy. And if you add that in, that strange kind of matter, you're actually able to fit the observations. So that's pretty powerful. You guys don't really want to see this, but basically the way you do it is you use the old tried and true equation. It's not written quite nicely here, but basically it's v squared equals gm over r, where g is the gravitational constant, then the mass of the galaxy internal to your rotating distance, and then the radius, the distance you are from the center. And when you do all this and you wave your hands a little bit, you find out that the mass to light ratio is 10 in 10 solar units. In other words, there's about 90% of the mass that is missing in that spiral galaxy. Well, here's another thought, something that Andy and I have been throwing around left and right for a while, and I think we're actually going to do a debate on this. Which will be kind of fun. So you can imagine that, yes, okay, you need more mass to make these galaxies spin at the right rate. But there's another way to do it, and that is to modify these tried and true, never fail equations of force that Isaac Newton gave us. They have worked for us for 400 years, but maybe they don't work so well on very large scales like the size of a galaxy. And if you do that, and you imagine that the force of gravity does not drop off as 1 over r squared, but in fact drops off at 1 over r, 1 over the distance to the center of the galaxy, then you can fit this data pretty well. This modification is called modified Newtonian dynamics, or MOND. And you can see here the blue data points are in fact the rotation curve of a given galaxy. As you move outward from the center of the galaxy. The green line here is the fit to those data from MOND. The red line is the fit to that data from dark matter. And as you no doubt notice, MOND actually fits the data better than dark matter. So, an interesting addition to our thinking. Is there more strange material in the universe? Or do we just not understand quite how gravity behaves on large scales? Well, this is all a result of observing galaxies, and there are, we now believe, about 2 trillion galaxies in the universe. This is the Hubble Deep Field, about 2.7 by 2.7 arc minutes in diameter, and there are about 3,000 galaxies there. And they observed with Hubble even longer, integrating for many days on this one tiny patch of light, just like they did with the deep field for the ultra deep field. And I forget which one is which, but it has about maybe 10,000 galaxies. Here's the extreme deep field from Hubble with 5,000 galaxies and a very tiny, tiny, tiny piece of the sky. So there are enormous numbers of galaxies, and it's important to point out that in a universe that was completely flat and completely homogeneous in the beginning, you would have no galaxies. You would have no stars, no planets. Everything would be uniform, and yet we see this. We see galaxies forming. So we need to be able to explain this. And it turns out that dark matter is quite helpful in explaining this. Well, here's a nice graphic I found of a large-scale structure in the local universe. We've been able to map the positions and recession velocities of thousands, in fact, millions of galaxies to see what the structure of the universe looks like. And what you can see from this is that there are little structures in here. There are fine filaments that galaxies have gathered along. There are certain places where there appears to be not much matter. In fact, it's not homogeneous at all. And one explanation for this is that in the very early universe, and by that I mean a time period before about 380,000 years after the Big Bang, where light could eventually penetrate into the rest of the universe once atoms were able to form and the universe was cool enough, there were tiny, tiny, tiny fluctuations in density before that. And those tiny fluctuations in density grew into these large structures that you can see here. And in order for that to happen, you need to have a kind of a push-pull in the early universe between dark matter and the pressure of the radiation pressure that is caused by the very hot conditions of the very early universe. So that would be consistent with the presence of dark matter. Well, here's something else. It's kind of interesting. This is a picture of the Abell cluster, the Abell 370 cluster. This is a large cluster of galaxies that are acting as gravitational lenses for galaxies in the background, for much more distant galaxies. And this happens because, as Einstein predicted, through his theories of general relativity, matter warps space. So light will travel in a straight line as long as it can, and as it reaches parts of space that are curved from the matter around them, the light curves as well. And so we can see in here, you can see, for example, some of these streaks around the Abell cluster. Those are distorted images of background galaxies. And that is consistent with an understanding that galaxies formed around dark matter clumps and clusters of galaxies formed around larger dark matter clumps. And so this gravitational lensing effect is a way to probe not only the distant galaxies behind the cluster, but also the presence of dark matter to understand its distribution and its power to bend the light from those distant galaxies as it does. So this is all kind of good evidence for perhaps the existence of this funny kind of matter, except for MOND. So just to give you kind of a picture of what we're talking about, the universe begins as a very small, hot, dense singularity, if you will, expands very quickly through now what we believe is expansion theory, which explains why most of the universe, as we look in multiple directions, has the same remnant, roughly the same remnant energy. And as the universe continues to expand and cool down, we reach this time that is circled here, where the universe is cooled enough that atoms can form and attract electrons. And at that point, electron scattering diminishes, and the light from the early universe can get out. That light is kind of the pressure imbalances in the early universe, this fight between dark matter and the pressure of this very hot plasma, get frozen into that signature at that point. And from there, the universe begins its expansion. that remnant energy that from the expansion of the universe, it was predicted actually before it was observed, and that is that if the universe was once very hot, it should now be rather cool as things have expanded. Expanding things cool. And so this is the cosmic microwave background radiation, or CMBR, or sometimes just CMB. This is a picture of that very consistent temperature background radiation of the universe from the COBE mission, Cosmic Background Explorer, that won a few Nobel Prizes, as a matter of fact. And this is indicating a temperature of around 3 degrees Kelvin. Okay. However, we have different instruments on the COBE spacecraft were able to find some anisotropies, some changes in temperature over certain angular distances. And we have then sent even better spacecraft, the WMAP, Wilkinson Microwave Anisotropy Probe, and the European Planck spacecraft to look with higher resolution at these temperature differences in the cosmic microwave background radiation, which it turns out is actually radiating at a temperature of about 2.73 degrees Kelvin. Here again is our picture of the formation and evolution of the universe, basically showing this period of first light where atoms could form, and the expansion that has happened rather rapidly initially, even though it's fighting the tug of matter. But in this more recent epoch, the density of matter in the universe has decreased because there's a certain amount of it and the universe is bigger. And so we find that this tug between dark matter and what we will call dark energy, that we will get to later, is now being won by dark energy, and the universe is accelerating in its expansion. A lot of weird stuff here. So basically, the imprint of the early universe, of these tiny, tiny temperature fluctuations, got magnified into the temperature anisotropy that we see today as we look out in the microwave region and can map the temperature differences in the universe as we see it today. Now, here's where it gets a little crazy. All right. So we are able to see some of these very, very tiny temperature differences in the background radiation, cosmic background radiation, and we can plot these on an angular scale. So here we have a nice graphic where the angular size of these temperature differences is on the x-axis in units of degrees, and the temperature fluctuation itself is on the y-axis. So cosmologists can read this, what's called a power curve, like an oracle, to determine some of the most important features of the universe, including how much matter there is, baryonic matter versus dark matter and dark energy, and the general geometry of the universe. Is it flat or curved? These peaks in the power spectrum reveal the overall density of ordinary matter in the universe and describe the effect of ordinary matter on the oscillations in the early universe, this push-pull between the dark matter and the pressure of the hot plasma. So let me go to the next slide here. Okay. So how does this work? So we're looking at the universe, background temperature of the universe, this 2.7 degree Kelvin background radiation, and plotting it versus the angular size of the temperature differences. And right around 1 degree, it's actually 0.8 degrees in size, you see a large peak in this power curve. And that peak was predicted before it was observed. And the size of that peak, the height of that peak, indicates whether we have a flat universe or a curved universe. And it turns out that right around 1 degree of angular scale here is what you would predict for an essentially, approximately flat universe. And by that I mean that parallel lines go on and never cross. Okay? So that's one of the outcomes of the power spectrum. However, there are 2 other peaks here at smaller angular sizes. And these other peaks tell us a little bit about the proportion of dark matter to baryonic matter. When I say baryonic matter, I mean the matter that makes up you and me, the matter that's made of baryons and neutrons and protons, and the matter that makes up all the things that we can see. And the higher that third peak is versus the second peak, the larger the distribution of dark matter is in the universe to regular baryonic matter. And it turns out that the best fit to this power curve is achieved by using the cold dark matter model, which includes a significant component of dark matter. So that's a very powerful piece of evidence, perhaps the most powerful piece of evidence supporting the existence of this bizarre material, this bizarre dark matter material. One other piece of evidence I want to show you is, as we've talked about, matter in the universe is not distributed equally. It's dominated by clusters and superclusters and large filaments of cluster. This is a model that was created from observations of the what I'll just call the near universe. You can see the scale here of 125 megaparsecs, and it's also contains these voids, places where there doesn't appear to be very much matter. These galaxy superclusters appear to be at the top of this hierarchy. Inside those, we have galaxy clusters and individual galaxies and solar systems and so on. And this whole structure that we see here is called the cosmic web. So as we've mentioned, a completely homogeneous universe would have no cosmic web. There would be no galaxy clusters or galaxies or stars or planets. Everything would be homogeneous. But as it turns out, when the universe began, the universe was almost completely homogeneous, with tiny density fluctuations, which were the seeds, which became the seeds of everything that we see in the sky. The result is this large-scale structure that we see, and it's essentially a map of those tiny primordial fluctuations. So this is evidence for cold dark matter in the larger universe that would have to have been present in the early universe in order for this structure to be visible today. So I think that may be all I want to say right now. Yes. Okay. So we're going to leave that. We're going to leave our audience here with those pieces of rather salacious evidence, some that support the existence of dark matter, and in fact, one that says you don't need it. And we will be talking about this formation and evolution of the universe with dark energy and other processes in later shows. So I'll stop there.
Thank you very much, Lou. That was really interesting, and I hope you can carry on with that. As Lou mentioned earlier, he and I decided we're going to have a debate, dark matter versus MOND, and he'll be in the red corner, I'll be in the blue corner, and we're going to get that sorted out as soon as Lou has the time available, I guess. So,
well, I'm already on Lou's side, so that was a perfect fit almost, wasn't it?
We need somebody on a third side that is neither dark matter nor MOND.
Oh, 6 of us. So.
Will this discussion be held in a cage?
Yeah,
lack
Kate.
of understanding.
Yeah.
The question is, does it
I see
matter?
you as far apart as you can be.
Yeah.
I
Does
see you
it
both as
matter?
far apart as you
No.
can be on the screen.
Well,
But
Anyway.
I was thinking you were talking about Mond, and you showed the comparison between dark matter and the Mond. But isn't there a problem that once you start to expand into bigger structures, that the Mond tends to fall down a little bit?
Yeah.
Mond does a better job than the lambda cold dark matter model in defining what we see as rotation curves of individual galaxies. It does, but does a slightly poorer job than cold dark matter in defining the rotation velocities of galaxy clusters. And then, of course, you have the problem of gravitational lensing, which I understand can be explained away with Mond, but is a little more difficult. So
there we are.
It's all there to be discovered.
Yeah, you mentioned the cosmic web. That's not the only web in the universe, of course, because we have the James Webb.
Oh,
Sorry.
well said. Well said.
Anyway, Lou and I will be debating dark matter versus Mond. As soon as Lou's got the time available to do it, we will have a good old chat about it. So I hope you look forward to that.
Let's plan it out maybe a couple of weeks. I think I'll be able to.
Yeah.
Okay.
Headlining in Las Vegas.
We'll put it
It's a
together.
great
for you.
debate.
Don't forget, if you have any questions about any of that or anything you see on Space Oddities, put them in the chat or put them in the comments after the transmission today. It really helps us if you comment on YouTube about the video. It really helps us because it gets the YouTube algorithm to pay us more attention. I'd be very grateful if you didn't make comments like the one we had earlier in the video. Somebody just wrote, "Why are all those guys so old?"
Oh no!
What do you know? I graduated high school.
I know. So
A few more of us, we could be like an advent calendar, couldn't we? Be like an advent calendar. A few more.
Yeah.
We might just mention Joram says has a comment here about tachyons, and
I think that was Sam, Lou.
Interestingly, I worked with a man. I think his last name is Newport at Goddard Space Flight Center when I was in high school, who took a sabbatical to go kind of study these things. And tachyons are theoretical particles that have not been observed yet, but the idea is that if you apply an infinite force to them, they travel as slow as they can, which is the speed of light. And as you back that force off, they travel faster and faster until no force provides an infinite velocity to them. So they are either not moving at all in time or moving backwards in time. And they're very interesting little thought processes.
Okay.
So,
Eons. Right. Oh, we seem to have lost Andy. He's gone.
he's sick of the whole thing, I'm sure. It's how does this
Somebody's
help you with your grocery
somebody's
prices?
cat was meowing.
yeah.
Sorry,
Somebody's cat was meowing. So
That is cat.
Okay, then he's back. He's back.
Yeah, sorry about that. There's a cat meowing frantically.
Oh, I'm sorry. That's my cat.
Oh, it's yours. That's where it's coming from.
How?
Trust you.
There she is. She wants my attention. I've been.
But it must be my 3D sound enhancement. It sounded like it was coming from another room. Yeah. What was this about getting old? Yeah. Right.
Yeah.
Okay. So anyway, big thanks to
Lou.
Lou.
Yeah.
Yes. You will be carrying on next week with this series of presentations. I trust you. What have we got for next week?
Well, we have to. I posed the question of dark energy. I think we'd better explore it.
Dark energy next week. So be it.
That's a good one.
Okay.
Even more controversial.
Yes, indeed. I'll be touching on related things relating to what Lou's been describing in the news, because we've got a couple of news stories that are related to that. Every week there are news stories relating to Mond and dark matter. So a couple of things in the news. Speaking of which, the news. So let's let's Lou's dematerialized. He's gone teaching. So anyway, let's move on with the news. Just give me a second to sort this out, and we will have a look at the news. Got quite a lot of news this week because I held some back from last week because I can't remember why, but we were there was some reason. Anyway, this is
live
the
launch, wasn't it? It was a live launch. We were rushing to get that sorted.
Absolutely. So so there we are. I hope you can all see that. And just let me sort myself out here. So this is the news for this week. Quite a few news items. The first news item concerns the world of steam. Now, this is not, as you might think, a train spotter's theme park. It is, in fact, news of a very, very interesting planet that's been discovered, quite groundbreaking. And this comes courtesy of nanoverk.com. This is a planet that's 100 light years away, and it's unlike any we've seen before. It's got the rather catchy name of GJ9827d. It's roughly twice the size of the Earth, and it's got an atmosphere composed almost entirely of water vapor, which is very, very interesting. It's the first time we've ever seen something like this, said Ishan Raul, who analyzed the JWST data as an undergraduate student at the University of Michigan. To be clear, he said, this planet isn't hospitable to at least the types of life that we're familiar with on Earth. The planet appears to be made mainly of hot water vapor, making it something we're calling, predictably, a steam world. Astronomers have long theorized that such planets might exist, but this study represents the first observational confirmation of a steam world. And although GJ9827d can't support life as we know it, discovering its unique atmosphere opens new possibilities for studying other small planets and their potential to host life. Now, the interesting thing about it is, to date, almost all exoplanets with measured atmospheres are mainly made of the lightest elements, that is hydrogen and helium, like Jupiter and Saturn, for example. But they are very different from the sort of life-enabling environment that we have on the Earth. Now, this steam world is the first planet we found where there's an atmosphere rich in heavy molecules, like the terrestrial planets of the solar system. So this is a huge step forward, and very, very unusual world. So here we are, the first world of steam, and that's obviously an artist's impression. Now, moving on from what Lou was saying earlier, there's been quite an interesting discovery made by the Webb telescope. Well, that's nothing new, of course, because it seems every day there's a new interesting discovery made by the James Webb Space Telescope, and of course that's what it was designed to do. Now, just to step back a bit, you've probably seen in the news lots of headlines all over the place saying that discoveries by the James Webb invalidate the Big Bang and all this nonsense. Of course, it's all nonsense. There's nothing that the JWST has discovered which in any way invalidates Big Bang theory. What is the contention is that we're seeing galaxies that existed very young in the universe within the first billion years that are more mature, more massive, and more luminous than can be accounted for by the theory of lambda CDM, which was what Lou was talking about. Now, lambda CDM gives us the history of the universe, and it establishes an evolutionary course for the early galaxies. So there are many reasons why some of the Webb discoveries initially were misrepresented unintentionally, because astronomers were saying these galaxies are X number of million years old and they are this distance and they have this mass. But on closer examination of the data, it turns out that there are reasons why a galaxy might appear to be more massive, more luminous, and more distant than than can be accounted for. And these include things like if you have a galaxy that's got a supermassive black hole at its center, there can be a lot of activity associated with that. Radiation in X-rays right across the electromagnetic spectrum, which can make the galaxy appear brighter than it actually is, and thus more mature, in other words, containing more stars. Another reason might be that a galaxy is full of dust, and that dust sort of reflects and refracts the light from the stars, making it appear there are more stars than there actually are. And in terms of mass, again, the supermassive black hole can make a galaxy appear more massive than it actually is if you look at just the stars. So there are all sorts of these things that can mislead. But this week, it was announced, well, last week actually, the red monsters. And this is an actual web image of the 3 red monsters. Not the background isn't. The background is not a part of the image, but the 3 objects here are now known as the 3 red monsters. And these galaxies are almost the size of the Milky Way, and they were already in existence 1 billion years after the Big Bang. Now, you know, that sounds a long time, but in the 14 billion year history of the universe, it's not, obviously. So how did these monsters grow so large so quickly? And they appear red in the JWST images due to their large dust content, which makes them absorb shorter wavelengths of light and scatter the remaining light into longish reddish wavelengths. And the web has shown that these galaxies, interestingly, produce stars at about 2 to 3 times more efficiently than galaxies in the later universe. What do we mean by efficiently? Well, it's to do with the fact that galaxies contain X amount of gas. What percentage of that gas at a point in time was being converted into stars? And these galaxies have an efficiency of about 50%. And in today's universe, galaxies typically have an efficiency of about 20%. So this suggests that the early universe may have had a different set of conditions that allowed for much faster and more efficient galaxy growth. Why? This is a mystery. It may be based on factors such as more abundant gas. There was just more gas around. The gas cooled faster, other conditions that are not yet understood. But interestingly, getting back to what Lou was talking about earlier, these galaxies are not predicted by the dark matter idea of the universe, the lambda CDM history of the universe. But these galaxies are exactly predicted, guess what, by MOND. So this is another sort of confirmation that MOND was dominant in the early universe rather than the effects of dark matter that we thought we understood. So again, you know, it's MOND or dark matter, and this enormous conundrum that Lou and I are going to have a debate about in a couple of weeks. So I just thought I'd mention that because you know, this was completely unexpected. These galaxies just don't follow the rules of lambda CDM, but they do follow the rules of MOND. They are predicted by MOND, these galaxies that are this big, this massive, and this luminous in the universe. Okay, let's now move on to everybody's favorite subject, black holes. Now, scientists using observations, this is from science.nasa.gov, scientists using observations from NASA's Neil Gehrels Swiss Observatory have discovered for the first time the signal from a pair of monster black holes disrupting a cloud of gas in the center of a galaxy. So this is 2 supermassive black holes at the center of a galaxy, co-orbiting, going around each other. Sorry about that. Let's put that back. It's a very weird event. It has the rather catchy name again of 82021 HDR. That keeps recurring every few months, said Lorena Hernandez Garcia, an astrophysicist at the Millennium Institute of Astrophysics, the Millennium Nucleus on Transversal Research and Technology to Explore Supermassive Black Holes, and University of Valparaiso in Chile. We think that a gas cloud engulfed the black holes, As they orbit each other, the black holes interact with the cloud, perturbing and consuming its gas. This produces an oscillating pattern in the light from the system. And she published a paper on November the 13th in the journal Astronomy and Astrophysics. And these two black holes are in the center of a galaxy called, and again, really catchy name, 2MAS X J212240027 plus 3409114, located about 1 billion light years away in the constellation of Cygnus. And the two black holes are about 16 billion miles or 26 billion kilometers apart, close enough that they're only a light day apart. And together they contain 40 million times the mass of the sun. And these orbits are the co-orbiting black holes. They complete one orbit around each other every 130 days. And they're going to collide and merge very soon in about 70,000 years. So since the first flare, the center has detected outbursts every 60 to 90 days. Hernandez Garcia and her team have been observing the source with the SWIFT telescope since November 2022, so exactly 2 years. SWIFT helped them determine that the binary system produces oscillations in ultraviolet and X-rays on the same time that they see them in the visible range. So it all happens at the same time. The researchers conducted a Goldilocks type elimination of different models to explain what they saw in the data. Initially, they thought the signal could be the byproduct of normal activity in the galactic center, and then they discovered whether a tidal disruption event, which is when a star gets torn apart by a black hole, could be the cause. Finally, they settled on another possibility, the tidal disruption of a gas cloud, one that was bigger than the binary itself. When the cloud encountered the black holes, gravity ripped it apart, forming filaments around the pair, and friction started to heat it. The gas got particularly dense and hot close to the black holes. As the binary orbits, the complex interplay of forces ejects some of the gas from the system on each rotation, and this produces the fluctuating light that the telescope and the observing center have seen. So that is a really interesting set of observations. And we know that these supermassive black holes, they come about orbiting each other because of a collision of two galaxies, both having supermassive black holes that come together at the center under the influence of gravity, co-orbit each other for maybe millions of years, and then eventually merge. Now, we can't see those mergers happening because when black holes merge, there's no explosion, there's no light release, there's nothing. But we can detect them in gravitational waves, although not with our current technology. We're going to have to wait till the 2030s, till the European LISA gravitational wave telescope or array is launched, which will be sensitive to these low frequency gravitational waves caused by the merging of supermassive black holes. Okay, so moving on. Okay, just a little news story, starfish and otters. This is just a bit of space exploration news, well, satellite news really. Satellite servicing Starfish, sorry, I'm on all teeth tonight. Starfish Space announced that it has raised $29 million in a new funding round led by Shield Capital. Starfish Space, founded by former Blue Origin and NASA engineers, develops autonomous satellite servicing vehicles for extending satellite lifespans and, importantly, removing space debris. That's what they're working on. The company's gained traction recently, securing a $37.5 million US Space Force contract and deals with commercial satellite operator Intelsat and with NASA. The completion of the new round brings Starfish's total fund to date to over $50 million. They're based in Washington, and they've developed an in-space servicing vehicle called, predictably, the Otter. The new funding will enable Starfish to complete the development of the first 3 Otter vehicles, which will perform missions for Intelsat, the US Space Force, and NASA. And they're due to launch in 2026. So this is a vehicle that's actually going to service satellites in orbit. But I think we're all more interested in the idea that it's also being designed to collect space debris. So there we have it. So that's the starfish and the otters. Good news for the Roman Space Telescope. The telescope has been delivered. So we're one step closer towards launch. The optical telescope assembly, which has got a 7.9 foot or 2.4 meter primary mirror, which you can see here, was delivered on November the 7th to the largest clean room at NASA's Goddard Space Flight Center in Greenbelt, Maryland, where the observatory is being built. The telescope will focus cosmic light and send it to Roman's instruments, revealing many billions of objects strewn throughout space and time. Using the wide field instrument, a 300 megapixel infrared camera, astronomers will survey the cosmos all the way from the outskirts of our solar system towards the edge of the observable universe. They're going to use the coronagraph on the Roman telescope to test new technologies for dimming host stars to image their planets, because obviously when you're looking for exoplanets and you want to image them directly, you need to block out the light from the star, otherwise you won't see anything. And they're going to test the technology for doing that, new ways of doing that with the telescope. We have a top-notch telescope that's well aligned and has great optical performance at the cold temperatures it will see in space, said Bente Ekholm, optics lead for Roman's optical telescope assembly at NASA Goddard. I'm now looking forward to the next phase, where the telescope and instruments will be put together to form the Roman Observatory. And if I remember rightly, the Roman Observatory is due for launch towards the middle of next year, if I remember rightly. So this is good news for the Roman telescope. The telescope itself actually was donated by the US military. It's a sort of a spare they had. These are the sorts of telescopes they use in their spy satellites. So just remember that when you go out on the street, you've probably got a few of these size mirrors peering down at you from orbit. Okay. Going now to the moon, the first samples from the far side of the moon contain signs of surprising volcanic activity near the lunar south pole. Two separate analyses of lunar rocks brought to Earth by China's Chang'e 6 spacecraft show the rocks formed from cooling magma relatively recently. And we're talking about 2 billion years ago. That is relatively recently, according to papers published last week in Science and Nature. The measurements may help solve the mystery of why the moon's far side is so different from its near side, but also raise new questions about the history of lunar volcanism. The moon's two faces are like night and day, with different topography, chemical composition, crater density, and evidence for volcanism. Huge solidified pools of lava called mare cover almost a third of the near side, but only about 2% of the far side shows signs of flowing lava. The enigmatic asymmetry between the near side and the far side of the moon is a long-standing unresolved conundrum. Geochemist Q. Li of the Chinese Academy of Sciences writes in the Nature magazine. Until recently, all rocks humans had brought back from the moon, of course, from the Apollo missions, were from the near side. Samples from the Apollo and lunar missions in the 60s and 70s suggested the moon was most volcanically active around 4 billion years ago and had mostly cooled by about 3 billion years ago. Rocks from Chang'e 5, however, show more recent volcanism around 2 billion years ago. But the volcanic history of the far side was a complete mystery until Chang'e 6 returned the first samples from the south pole of the moon. The spacecraft came back to Earth with almost 2 kilograms of lunar soil from the South Pole Aitken Basin, which, as you may know, is the oldest and bigger crater on the moon. And it's the source of most of the volcanic material on the moon's far side. Imagine having rock samples from maybe 10 locations in North America, and that's what you know about Earth, says planetary scientist Stephen Ellardo of the University of Florida, who was not involved in this work. Then all of a sudden, you get your first rocks from South Africa or Australia. Now you get to have that as another data point to learn about the whole planet. And that's basically what this is for the moon. And that story comes from sciencenews.org. So the history of lunar volcanism again, we thought we knew what it was, but it turns out to have, the moon turns out to have been volcanic much more recently than we actually thought. So that's good. Very interesting. Moving on now, a company called Impulse Space has purchased 3 Falcon 9 launches for its Helio transfer vehicle for missions starting in 2026, including one for the US Space Force. The company announced last week it signed a contract with SpaceX for the Falcon 9 launches. Each launch will carry the company's Helios transfer vehicle, a high-energy kick stage the company introduced in January to transport payloads quickly between orbits. So that's good news for Impulse Space, picking up those contracts. And now we move to Mars. Now, about 11 million years ago, this is from Sci.News, by the way, an asteroid struck Mars about 11 million years ago and sent pieces of the planet hurtling through space. One of these chunks eventually landed on the Earth, crashed into the Earth. During early investigations of this object, and this object is called the Lafayette meteorite, scientists discovered that it had interacted with liquid water while on Mars. Now, researchers from the United States and the United Kingdom have determined the age of the minerals in the meteorite that formed when there was liquid water. We can identify meteorites by studying what minerals are present in them and the relationships between these minerals inside the meteorite, said Dr. Marissy Tremblay, a researcher at Purdue University. Meteorites are often denser than Earth rocks, contain metal, and are magnetic. We can also look at things like a fusion crust that forms during entry into the atmosphere. And finally, we can use the chemistry of meteorites, specifically their oxygen isotope composition, to fingerprint which planetary body they came from or which type of meteorite it belongs to. According to the authors, some Martian meteorites, such as the Lafayette meteorite, contain minerals that formed through interaction with liquid water while still on Mars. Dating these minerals can therefore tell us when there was liquid water at or near the surface of Mars in the planet's geological past, Dr. Tremblay said. We dated these minerals in the Martian meteorite Lafayette and found that they formed 742 million years ago. Now, we don't think there was abundant liquid water on the surface of Mars at this time. It's too recent, really, because we think that, you know, most, if not all of the Martian water disappeared billions of years ago and either faded away into space or went underground, because we now know that there's a lot of Martian water underground. She continued, instead, we think the water came from the melting of nearby permafrost, and that the permafrost melting was caused by magmatic activity that still occurs periodically on Mars to the present day. So what she's saying is volcanism melted the permafrost, and that activity, we think, is still going on today. Very interesting story, this Martian water in this meteorite being dated to 742 million years ago. We're staying with Mars. If you look at this image, look at the unusual white rocks in the foreground that the Perseverance rover has found. And this is on the rim of Jezero crater on Mars. And they actually diverted the rover to explore this strange scattered field of bright white rocks, which obviously sparked the interest of the scientists. This story is from astrobiology.com. And Perseverance has been climbing up the steep slopes of Jezero crater for over 2 months, and it's a really steep climb. It's a really difficult job for this rover to get up onto the crater rim, but it's making good progress. And ever since they approached the edge of the crater, it's been seeing really diverse and strange looking rock. Do you remember that one I showed you a few weeks ago, the zebra rock, the black and white striped rock? Now there's an inlet channel in the wall of the crater that water flowed through, or out of, should I say. Near that, there's a whole host of colorful boulders, and more recently, this zebra striped rock. But obviously the crater rim hasn't finished delivering surprises yet, though. And just as we were preparing for Halloween, Perseverance discovered this field of bright rocks. And what we can say about this is that on the Earth we find white rocks, obviously in a wide array of geological settings. Actually, my daughter brought me home some white rocks today that she collected in the forest on her way home from school. She's always bringing me stuff. She's been bringing me acorns forever. I've got so many acorns now. I think I could start an oak forest. Anyway, I digress. And you know, there are lots of minerals on the Earth that can create these white rocks. On Mars, however, with its lack of plate tectonics and basaltic crust dominated by dark minerals like olivine and pyroxene, white rocks on Mars are a rare find. And they planned several observations to examine these rocks, including multispectral imaging with the rover's Mastcam Z and zapping them with its SuperCam laser. Hopefully, these observations can shed light on how these white rocks formed all the way up there on the crater rim. Unfortunately, none of the rocks were big enough to safely inspect them up close with the microscopes on the robotic arm of Perseverance. So they're on the lookout for bigger examples of these white rocks that they can put the robotic arm out to and examine in great detail. And of course, the mystery is, how did those rocks get there? They're called float rocks, by the way. And in geological terms, float rocks are rocks that are not in their loose rocks that are not in their original location. In other words, they've been transported there somehow. They didn't form there. And the whole field of these white rocks is just over a few square meters. So again, interesting stuff from Mars. Now, you may remember, or you may know, that SpaceX have had a lot of problems with the Federal Aviation Authority certifying their flights and giving them licenses for their Starship program. And there's some good news. The FAA have actually now formed a committee which is meant to expedite these licenses much quicker than they have been. Now, of course, the FAA is used to the very, very slow launch cadence of NASA, just a few times a year. They're not funded nor equipped nor staffed to the levels necessary to process rapid launch licenses, because SpaceX are launching their Falcons every few days. It was only a couple of weeks between the IFT-5 and IFT-6 tests of the Starship. Oh, by the way, while I remember, the next test of the Starship is now confirmed for January the 11th, 2025. So we'll be covering that live if we possibly can. But they've set up this committee now to try and process the paperwork a lot quicker, which is very good news. And they've been under a lot of pressure from Congress. There've been congressional hearings and investigations, and basically they haven't got enough staff because they can't attract enough engineers in the US. And being a US government agency, they're not allowed to recruit from overseas. So it's not really the FAA's fault. So let's hope this breaks the bottleneck, although you'll forgive my skepticism whenever I hear the phrase "a committee has been set up," because it normally means that's going to slow things down, not speed things up. However, we will see. Moving on now to another related news item about this whole business of the Hubble constant. You may remember that the Hubble constant is this conflict whereby if you measure the rate of expansion in the universe with two different methods, you get two different answers. Those methods are the one that Lou was talking about earlier, the cosmic microwave background. The other one is measuring the light from distant supernovae. And there's what's called the Hubble tension between the two, because you get different answers using the two methods. Now, astronomers and scientists have examined the methodology for measuring the rate of expansion of the universe with supernovae and doing the same thing for the CMB. No mistakes have been found after exhaustive investigations in either methodology. So something weird's going on. So in comes, at this point, the South Pole Telescope, which is what you're looking at the moment, and it is at the South Pole. And they've been doing a really, really detailed survey of the cosmic microwave background to try and, if possible, shed some light, no pun intended, on the value for the Hubble constant. And what they found is that their measurements agree entirely with previous measurements arrived at by measuring the light from the cosmic microwave background. So this confirms that the method of using the cosmic microwave background to measure the rate of expansion of the universe looks to be 100% rock solid. So attention now must fall on the supernova method, which at the moment is also looking rock solid. We have no idea why there's a difference in the Hubble constant. And this is important because, you know, the Hubble constant dictates the whole history of the universe, really, the rate of expansion. So it's very important that we narrow down what the exact value is. One suggestion, bizarrely, is that the universe is expanding at different rates in different directions. And this could be why we're getting different values depending where we look. And that's a really bizarre suggestion. And I don't think that's taken seriously at the moment, but it is nonetheless a possibility. So we live in interesting times, viewers, very interesting times. Okay, lastly today in the news, I don't know whether you remember the Chinese Zhurong rover on Mars, another Martian story. They found evidence of a Martian shoreline, and it streaks through Mars's northern hemisphere. And this offers fresh support to the decades-old hypothesis that an ancient ocean covered the Martian northern hemisphere billions of years ago. And Zhurong landed in 2021 in one of the largest and oldest impact basins on Mars, known as Utopia Planitia. Traveled about, didn't go very far, about 1.5 miles, studying the geology as it went, looking for signs of water or ice, and combining observations from the onboard cameras and ground penetrating radar and remote sensing data from orbiting satellites. Bo Wu at Hong Kong Polytechnic University and his colleagues spotted several water-related features around the rover's landing area. They included crater-like pitted cones, troughs, sediment channels, and mud volcano formations that the team interprets as evidence of an ancient coastline. Based on the composition of surface deposits in the area, the ocean likely existed around 3.68 billion years ago, according to a paper that they've written about it. And the team thinks a variety of water-related minerals, such as hydrated silica, started forming on the ocean bed around this time. The water was heavily silted, forming the layering structure of the deposits, studied co-author Sergei Krasnikov of the Hong Kong Polytechnic told Reuters. The ocean then froze for about 10,000 to 100,000 years, a relatively short period, etching out the observed coastline before drying out roughly 260 million years later. So this is good news, because this old idea that much of the northern hemisphere of Mars was covered with an ocean, they could have found the shoreline of that ocean. So that's incredibly good news. Anyway, that's the news for this week. I hope you enjoyed that. There you are. Anybody on the panel want to say anything about any of those? No? Okay, we'll move on then. Okay. More news next week. So what we'll do now...
Andy, can you hear me?
Yes, I can.
Oh, sorry, I was trying to attract your attention, but obviously you couldn't hear me. Yeah, just a couple of points. You know, you were talking in the second article, I think it was, about with the James Webb finding the 3 monster galaxies.
Yeah.
And they seem to prove the MOND. I was just wondering, because we've also got, when we talk about the expansion of the universe, the expansion was quite even for quite a long time. Then we got to just over 10 billion years, sorry. And then there was this extended expansion. It increased. Do you possibly reckon, I mean, I'm just hypothesizing, I'm talking at me backside possibly, but in the early, possibly in the early universe, MOND was the dominant factor. But when it came to the great expansion, about just over 10 billion, just over 10 billion, not 10 billion years ago, at 10 billion years, do you think then possibly cold dark matter could have possibly gained the upper hand? And this is why we get...
Yes. I suppose. Look, it's. I think a lot of people are slowly coming around to the idea.
Why would there be a?
I think
Why would there be a change though? And what would change it?
Well, we know. I think it was about 6 billion years after the Big Bang.
Oh, was it? Sorry.
Yeah, yeah. Well, it's 4 billion years between friends. I think something happened 6 billion years after the Big Bang, and dark energy reversed the slowdown of the universe's expansion and started accelerating it. Now, it's thought that this was some sort of, I don't know, phase transition, something weird that we may not even ever be able to comprehend. And we certainly don't have any evidence left in the universe of it. So it's not something we could ever observe. But something happened 6 billion years after the Big Bang, that dark energy overcame the arresting force of gravity and started accelerating the universe again. Now, recent studies, as I think I talked about, was it last week or the week before? Recent studies have shown, in fact, that we've always thought that that rate of expansion due to dark energy was constant. And the density of dark energy was constant. But in fact, due to some findings of the DESI instrument in America, which is an array of small telescopes that's been studying dark energy, the density of dark energy has changed over time. But why it gained the upper hand 6 billion years after the Big Bang, we don't know. Now, it's long been thought. A lot of people are sort of thinking, well, hang on, what if the answer is neither dark matter and MOND, but a combination of both? So, you know, but, you know, the basic thing about MOND is that it says that gravity behaves differently to what we think at large scales, at large distances. And we don't know why that would be. But you know, the MOND enthusiasts say, well, it just is, you know, don't know how, but it just behaves differently. So yes, very interesting questions.
Just to sort of like whether, like you said, there was the phase transition, as we call it, and I'm wondering whether or not if they do studies of MOND in the early universe and whether that was more the dominant. Possibly the dominant faction there, but then of course when we got to that expansion, there was a time when it changed, and then maybe the cold dark matter got the upper hand with the dark energy. I don't know. Just some of those. I'm probably talking at me backside. I don't know, but it's just one of those things.
No, I do appreciate your question, and I know what you're saying. But you see, the thing is, it's not a question of one getting the upper hand, because we have evidence for both of them still working in the universe today, depending what measurements you do. Yeah. So if you look at galactic rotation curves, dark matter explains those. But when you, but also MOND, there have been new findings that completely blow the dark matter idea of galactic rotation curves out of the water, which I'll probably report on next week because it's still fairly new and I need to research it a bit. But then you look at galaxy clusters, which is what Lou was saying earlier. You can't use MOND to predict how gravity works in galaxy clusters. It just doesn't work. It works for individual galaxies, but not for galaxy clusters.
No, galaxy clusters,
basically.
Yeah. And just another one. You were talking about.
Of course. Sorry. Just say, of course, there could be a third option which combines everything, couldn't it?
Yeah, exactly. Yeah.
Yeah.
We're definitely missing something somewhere.
Yeah.
And maybe one day we'll be able to resolve it. Or we've gone down a blind alley. We don't know. It could be something completely different.
If you think about it, we had Newtonian gravity, and that was, you know, an approximation, if you like, but it worked for everything that people were doing at the time, predicting the orbits of planets and whatever. That works fine. But then, of course, Einstein came along and said, well, no, there's a lot more to it than that. But, you know, we know that general relativity isn't complete. You know, scientists have been looking for new physics to demonstrate that there's more beyond general relativity. So who knows? Perhaps MOND is it. Just
sort of moving on a little bit. You mentioned starfish. Now, when I think of starfish, and satellites and things like that. I think of the the U.S. Air Force exploding a nuclear bomb in the atmosphere.
Oh yes, Project Starfish. Yes.
Project Starfish,
Oh,
and of
yeah.
course that destroyed their first satellite, Ariel 1, and also corrupted Telstar, which shortened its life because they didn't realize that the radiation was going to sit high up in the atmosphere, which of course the two satellites were passing through all the time.
Yeah. Yeah.
But yeah, that was an interest. That was just sort of a side note. But also the Starships. You're talking about Starship and the next launch. Of course, with I don't know if you read that or heard that with IFT-6, the test flight 6, as we know, the booster was directed to splash down in the Mexican Ocean, the Gulf of Mexico. And of course, we saw it actually explode at the time, and then we saw flames afterwards.
Yeah.
Well, apparently, it turns out there's a very strong suspicion that the SpaceX were able to scramble a fighter jet that actually flew out to the because it took it after hours of being there, it was still floating. So what they did is they scrambled a fighter jet from a local Air Force base, and they actually strafed it with bullets. They actually shot it to actually punch holes in it to get it to sink. But even then, it took quite a while to sink. But yeah, there's a video, and it's taken from the shore. It's not any SpaceX ones, and you see the booster lying there, and then all of a sudden you see all these white spots appear.
Yeah.
And they're saying that's where they were strafing it to try and sink it.
I think SpaceX have actually confirmed that now, that they had to. Yeah, they had to shoot it up to get it to sink.
Yeah. The only reason I saw it is because, and I guessed it was clickbait. They said, they shot the booster down. I thought they didn't shoot the booster
No, they didn't shoot it down. No.
No, but that's it. And I thought, well, I'll have a look and all that, because it's one of the more renowned sites, and they were just saying about how they strafed it while it was to make it sink. I thought that was quite interesting. That was quite worth a chuckle.
There's a lovely image that I saw earlier today with just the bottom end of the booster with the engines poking up out of the water.
Yeah, that's still...
Oh, I'm off. I've had enough.
But because it slowly sank. But they think they may retrieve it at some time. Just to get a better look at it and all that, but they had to sink it. There were several reasons. They said, "Oh, maybe we don't want our because I don't know if you saw when it actually sank and it went down. You could actually see the actual sides crumpling in.
Oh yeah,
they're so flimsy, and but they were saying they didn't want any of the interior exposed or all their rivals getting hold of anything. So
that stainless steel is only a couple of millimeters thick, isn't it?
Yeah, because I think they were. I can't remember. I think it's something like 6 millimeters thick, and they wanted to reduce it to 3 millimeters. So where they ended up, I'm not really sure. Because they wanted to lose a lot of weight, so maybe they compromised. But yeah, I mean, with the pressures as well, it's going to crumple anyway as it sinks. And all that.
Of course.
Thank you, Gerard, for your generosity.
Yeah, thank you, Gerard. Much appreciated. And thank you to
sorry, we're digressing.
So thank you very much, all of you, for your contributions. This will help because for us at Space Oddities, it's Bill's time of year, so this will really help. Okay, now before we move on to Roger, which is something I know everybody's just dying to do. No, maybe not. Not in this universe. So I just wanted to say a word about the Space Oddity. Sorry. I just wanted to say a word about the Space Oddities website, which I'm currently building. Now, I hope to get this up and running by Christmas. It's coming on really well. As part of the website, there will be a viewers gallery. And if you're a contributor to the viewers gallery, if you send us an image or images, what you will have on the website will be your own little section for your images, your own little gallery of your own images, with the details of each. Now, we would like to think that this will, open your wonderful work up to a bigger viewing public. So we think it'd be really good to do that. However, if you do not want your images to appear in the gallery on the Space Oddities website, when you send them in, please let us know. And obviously we won't include them, but it'll be a nice place where people can go to see your astro images. And, apart from obviously here on a Tuesday. So please let us know if you don't want your images to be included in the gallery, and we won't. It's as simple as that. Also, when we put your images up on the website, I'd like to stress that copyright at all time remains with you. You have the copyright on those images. And there's no option there will be no option on the website, because as I've turned it off, there's no option for people to download your images and share them and whatever. So, if you would like to have your own little gallery on the Space Oddities website to spread your fantastic work around, then fine. And if you don't, let us know. Simple as that. Okay. I'd like to move on now, and I think it's Roger's turn now.
Yay!
Yay! So, Roger, I gather we haven't got that big of gallery this week. Talking of the gallery,
No, we've got some, but there we are. It is what it is. But no doubt with the clearing skies that we will eventually get more images will come in at some point or other. So keep sending them in anyway.
Yeah, keep sending them in anyway. Gallery@spaceoddities.space is the address. 1 image per email, please. And if you could limit your resolution to 1920 by 1080 maximum, that would be much appreciated. So without further ado, let's have a look at what's up in the night sky with Roger.
Okay, so here we are working our way through November and into the start of December. Oh gosh, how time flies. But at the moment, we've got a waning crescent moon with a new moon over on Sunday. So things might be a bit better with the night skies, but then again, maybe not. I won't hold my breath. So we are looking at the night sky for through the week at midnight. And as you can see, Orion is gaining the dominance of the southern sky. And we've also got Jupiter quite well placed, and also Mars. So get those scopes out, cameras and whatever you need to do to get those pictures in, and we'll see what amazing pictures we can get from you. So we're currently experiencing that, and of course being around midnight, Saturn is now setting, so there we go. But during the early part of December, we do have Jupiter at its opposition, so another opportunity to have another look at that lovely planet. And just as the sun is setting, we've still got Venus and Mercury just above the horizon, although Mercury is even lower than you would like normally to see it, and getting quite close to the sun, but there we are. Venus is still being quite a stunning evening twilight object, so you can't really fail to miss it, as it's just past the southern horizon as it sets, as the sun sets. So keep an eye out for that. Won't need much opportunity to miss that. Okay. Oh, hang on. Comet Sunshine Atlas is pretty much had its day. I've still got it here. It's going from 8.9 from tonight to magnitude 10.4 by the latter part of December. So it's pretty much had its day. So goodbye to that comet, and hopefully there will be more to view in 2025. Okay, we do have a very small gallery, but there we go. We've got one from Kevin, another one of his amazing sun images. Unfortunately, low altitude sun and jet stream didn't help with this image, but then we know what Kevin's like with his images anyway, and we've got some amazing pictures.
That's lovely.
Yes, it's a good job that Pete Williamson isn't on tonight, because he doesn't like inverted images of the sun, and he doesn't like the word Philly prom. which was in Kevin's description. So that was a good bit of luck. Amazing pictures there. Although I have seen that there are some sunspots around today, but Daz might fill us in on that. And our second image is from Jerry DeLay of the Tadpoles Nebula. And it's usually with his regular setup, and this is what he has produced. And those tadpoles are quite
lovely
pronounced in this picture. Very nicely done. A nice bit of nebulosity all around it too. Well done. And unfortunately, our last picture is another glorious picture from Cornwall of the sky that he usually does so brilliantly well with his Canon and Samyang. And this is over East Lane, Delabole, his little haunt that he usually goes to. And it gives you an idea of the night sky there.
That's nice.
It's lovely, isn't
Very
it?
nice.
Very nice.
Incredible.
It's lovely. But they're all good images. I mean, you know.
I know.
Now,
if I go back to the description, he said this is where we've got Jupiter and the Pleiades all merged together here. And I'm guessing that it's up around that big bright streak coming up through. So it's quite interesting to see what the Pleiades look like as a streak. They're all grouped together there, sort of just right of centre there.
Yeah, is that Jupiter below it? The really thick.
Yeah,
line?
the really great bright line there. Yeah.
Yeah, if you follow it up, it's almost. You can see just a little group of Pleiades, can't you?
Yeah.
Yeah.
Yeah,
of course, if we'd left it, left it longer, he would have got the red streak of Mars coming up through as well. But that's another opportunity to take.
Yeah, lovely.
But well done there.
Well done, Lee.
And so that's the 3 images that we had just for this week. But there we go.
Well, there we are. So thank you very much for that, Roger.
Okay.
And
great images, though.
Yeah.
All very good. Yes. We always get good images from our viewers.
We get superb images always from our viewers. In case you're wondering, we never, ever have had an image submitted that we haven't actually shown. We've never looked at an image and thought, God, that's crap. We're not showing that.
Even mine.
No, we never. Even yours.
We'll have to start somewhere.
Actually, Ian, in your absence, we did have a meeting behind closed doors to discuss your images, and we took a vote. I won't tell you who voted against, but
I'm looking at the thing. But
we've never had an image that we haven't voted for. Yeah, exactly. Yeah, it's the usual suspects, isn't it? Yeah.
Point to yourself.
So anyway,
okay.
just before we move on this evening, viewers, just a word about Christmas. Now, as you may know, Christmas Day and New Year's Day both fall on a Wednesday this year, which means Christmas Eve and New Year's Eve logically fall on a Tuesday. We won't be running a show on Christmas Eve nor New Year's Eve for fairly obvious reasons. We probably wouldn't be in a state to do it. So we won't.
Speak for yourself.
Yeah, well, I am. There'll be no Space Oddities on Christmas Eve nor New Year's Eve this year, but we will be obviously here at other Tuesdays over the Christmas period. So sorry about that, but you know. Okay, so we're going to move on now to Daz.
Oh, okay. The fingers crossed.
Yeah. After last week, cross your legs as well, Daz.
Everything. Right, okay, here we go.
So,
can you see that?
Yes, indeed.
Can you see my cursor?
Indeed.
Yeah.
Excellent. Right, before we actually start with the actual review of what's happening the last, basically the couple of weeks, because I didn't do it last week, in fear of a repeat of the other presentation I did last week, which will Lee said soon as mended. But what one I've got here is, again, we've got the how I usually start the talk, and it's the sun that, as we left it last week, which is on the left hand side, that's the 19th, and then we've got the sun today, which is on the right hand side, which is the whatever day it is today. It's the 26th today. So as you can see, we did have quite a few active regions on the sun on the 19th on the left, but they all seem to, as you can see, they're quite small. They're spread out a little bit. But again, if you notice, the southern hemisphere, they're almost in a straight line across the bottom, and they're just below the equator. If we move to the right-hand side, today's picture, we've got probably just as many sunspots, but as you can see, some of them are big, very, very big. And there's promise of even more. Just as you can see, there's one circled on the eastern um, uh, eastern border there, and it looks as though it's going to be another one. Now, the problem we've got at the moment, and did say this the other week, is that at the moment we've got no space assets on the far side of the sun, so we can't actually see what is happening on the dark side of the sun, on the far side, the far side of the sun. So we can't predict what's actually going to come round the corner. The only way we can do it is through helioseismology. And of course, that's because the sun, it vibrates, and we can measure these vibrations within the sun itself. And that will, and through analyzing that, we can actually put some prediction on what we think is actually going to appear. And also, we use what's disappeared a week or 2 weeks ago, what should be coming around, and were these things growing when they disappeared off the western limb, so that when they come round on the eastern limb, we'll have a rough idea of what's going on. So basically, that's what I'm going to talk about now. Also, what I'm going to talk about now is that I think everybody knows what this is. This is what we call a butterfly diagram, and this is, as you can see there, it's daily sunspot area averaged over individual solar rotations. And what it is, it's measuring all the sunspots and their energy and all that over the cycles. As you can see, this goes from 1870, which is, Andy can tell us about that, all the way up to 2020. This is quite an old diagram, but as you can see, it actually shows us where the sunspots were on certain rotations all through the year. And it produces this lovely diagram. And as you can see, on the left-hand side, down the side, you've got, as you can see, it's actually, that's longitude. So you got go from 90 south 30 to 90 north with the equator through the middle. Now, as you can see, all of these sort of form the shape. All the sunspots start up at higher latitudes, usually around 30, usually about 30, 35 or 25 latitude as we start a cycle, and then they slowly move towards the equator. And this is why I mentioned that the what we're seeing on the sun at the moment, the sunspot, the active regions, are all beginning to line up on the towards the equator. And this is actually, this is how we know when we're actually getting towards the actual minimum, the maximum, and because everything moves towards the center. Now, if you notice, a lot of these, if you look at the ones in the center, these sunspots, they overlap the previous cycle. Now, that's important. I'll tell you about that just in a second. So that's what we're looking at, these sunspot cycles. So let's just move on. This is a close-up of between cycle 23 and 24, which was just the previous one. And it gives you a bit of a closer idea of what we're actually looking at. So these are all these circles and dots are all active regions and sunspots where they are all accumulated. And as you can see, again, they started up around 40 in the latitude, 40 degrees latitude. That's sort of like the outlier, but they're usually around about 30 to 35 they start off, and then as we go progress through the cycle, it comes down, and you can see they're getting closer and closer to the equator. And this is one of the things we're looking for. There are other things we look for, but that's one of the main things that if we see that, we know we're getting somewhere. Now, again, if you look at this, you can see 24. Some of these spots actually hang up, are overhanging the actual previous cycle, cycle 23. And this is because I'm just going to show you one more picture, slightly different. This is the same sort of diagram. You can see you've got sort of like almost slimlined uh, uh, butterflies, almost like moth shapes more than anything. And again, we've got latitude, and along the bottoms we've got the date. But if you notice, this is all in different colors. This is a helioseismology map. And again, as you can see, we're looking more at the colors as well. As you can see, we are overlapping the previous cycle. And this goes back to, if you remember, if you've followed me for quite a while, I've always told you that sunspots, individual sunspots, they come in pairs. They don't come on their own, they come in pairs. And the best way to describe it is that you see, if you look at the face of the sun, you've got the equator, and you've got the north and south hemispheres. Now, sunspots, just for argument's sake, sunspots in the northern hemisphere, they usually align. Let's put it this way: you've got what they call the lead polarity. So in the north, you will have the two sunspots, and the one that's highest towards the North Pole will have a north polarity, and the one below will have a south polarity, plus or minus. When you drop below the equator, that reverses. So what you get is the actual sunspot towards the south again is north, and the one near the equator is south. So they're actually reversed. And this is one of the things we watch for. We're watching for those polarities to swap, because when we get to the end of a cycle, those polarities of those sunspots will actually swap. So this is what, and again, we'll also get the magnetic polarity of the actual sun swap as well overall. So when we see these start to swap, we know we're coming close. Well, the other side, the next cycle is starting. So as I said, in the north, where it was north at the top, south at the bottom, it will then go to south at the top, north at the bottom. So they actually swap. They actually change over, and this is one of the again, another thing we're looking for a change of cycle. Well, what with they've helioseismologists, and also because what you've got to also remember is connecting both these sunspots, there is probably a magnetic field, which gives us those loops, those lovely loops, and so there's material moving in this loop and stuff like that. So what we're looking for is the magnetic polarities of these sunspots and waiting for them to change. Now, if you also remember, I said to you many moons ago that the north and the south hemispheres are not connected in any way. They're doing their own thing. And what you can get is that and this is what appears to have happened with this cycle, is the northern hemisphere has burnt itself out. It burnt itself out a couple of months ago. The sunspots on the northern hemisphere have dropped dramatically, but now we've got the southern hemisphere beginning to take on pick up the gauntlet, and this is why we're getting all these big sunspots, mostly along the bottom. We do get the odd outlier that will come across the top. We do get active regions along there, which can give us action. But if you notice it, the most of them will change because they are not connected in any way. And this can give us what we call in maximum a double peak. So the northern hemisphere will peak, then it will drop down, and the southern hemisphere will carry on, take on the mantle, and that will peak as well. And that's why we get this sort of what we call a double peak. And this is why the sunspot cycle maximum actually spreads out over sort of like 18 months to 2 years. And this is what we're going to see. We've probably got about another year of the actual maximum. And until we've actually see the whole profile, we can't actually put a date exactly where the actual maximum was. So this is what I was just saying. What the reason I'm mentioning this is now heliophysicists are now beginning to see sunspot regions with reversed polarities. So basically, what we're saying, even though we're in solar maximum for cycle 25, it appears that solar cycle 26 is already beginning. So I just thought I'd like to put that in there for you, just a bit of information, because you'll probably hear some people saying, "Oh, solar cycle's 26," and you probably don't understand it. So what we're seeing is some of these sunspots are already showing change polarities. So anyway, there we go. Oh, that shouldn't be there. That should be at the bottom. We'll have to come back to that. So again, we're back to this again. So what's been happening in the sun? As you can see, the sunspots are beginning to kick off again. We're getting bigger active regions. They've been giving us some interesting. Well, they flattered to deceived again. We've started really slow again. The beginning of the week and the week before, we had lots of flares, but they were all C class flares. And C class stands for common. They're not very big. There has been some action since Saturday. We've started to get some M-class flares popping off from these big regions 3906, 3905, and also from 3908. And we've also had, but if you look, there's obviously a region. If you look at 3908 on towards the eastern limb, if you look directly across on the right hand side, sun, you'll see 3909s over there. You think, well, what's that doing over there? That is obviously a region that has appeared since this one was 3908 was numbered. So this looks like it could be a region that's beginning to grow. It's got some way to reach the western limb, but they've actually designated a number. So they're probably expecting some stuff to happen from there at some time. And maybe when it goes around the other side of the sun, it will grow and we'll have some action before. So again, as I said, we've got most of the action on the southern hemisphere. And of course, we've got this other region which they've circled, which I should presume, just judging by it, will be 3910. So yeah, this is what we're expecting. And as I said, we can't really predict everything that's going on. We're making assumptions using helioseismology by measuring it's like measuring earthquakes on Earth, and to give us a clue of what's actually going on, and then and also using the information we had from a week to 2 weeks ago, what's actually passed across the face and disappeared around the back again. And I'll to give you an idea in a second. Right, so here we go. Now here's our synoptic. This is where we can see everything. Somebody sat down, drew this. They've marked everything on there using all the measurements and all the information they've received. All the dotted lines, as I said, are the neutral lines, and they separate positive and negative areas on the sun. The dark areas, the big dark areas, that's coronal holes, which of course give us enhanced wind. They are basically big cool spots where there's very little magnetism going on, so lots more of the actual energetic particles can escape, and that gives us our solar wind. You can see where we've got the active regions, and you've got the numbers underneath, and of course they correspond to what's at the top. And that's basically a prediction of what possibly flare action we're going to get. And underneath each number on the actual sun's face, you will see what they're predicting for each active region. So 3905, they're expecting a 5% chance that there's going to be X flares. So yeah, and as I said, from Saturday we actually started to get a few M-class flares starting to pop off. But there has been some action, and I'll just go through it now just to show you what's been going on. I don't think there's anything else on there, but again, you can see most of it's in the southern hemisphere. So let's move on. So here's our usual sun. This is a week in 30 seconds. You can see what's coming around on the eastern limb. There's things firing off on there. There's a couple of little things going off on the western limb as well as things disappear. And there's a few bits and bobs that are happening. There was a filament lift just a second ago. And you can see it's all being indicated for you of what's actually going on. So this is the sun in 304, which is the red sun. Now this is 131. As you can see, we start off and there's not a lot going on. This is where we see the actual flares. You see one or two going off, but it's not until we get to sort of like a third of the way through, or possibly a bit more, that we will actually start to see some bigger flares popping off. So basically, the best thing to do, there is, if you look on the eastern limb, as they're coming around, you'll start to see some of the big flares go off. There are one or two on the other areas of the sun, but as you can see, it's all beginning. The action is all beginning to happen on the eastern side, and there are. We can even see that flare there that you just saw was beyond the actual limb, and that's what's coming around. I think that's what they've circled. This is just to show you the what's happening, what's been happening. Shows you the ejections. Now, when we get halfway through, now, bang! Did you see all that snow? That was a massive eruption, and they think it was 3889, our old friend, firing off a massive flare on the backside of the sun, and it created what we would normally say it was a 360 halo. But what you've got to remember is the sun is a sphere; it's not a two dynamic thing. So that the shock wave has gone all the way around the sun, and it's thrown a lot of highly energized particles at us, and it's created all that snow. We'll have a closer look at that in a second. In fact, this is it here. So this is a cactus version. I will start that again because it's quite quick. Bang, there it is. And look at all that snow that's coming. And a lot of that came towards us. But there was no massive CME. If it was a CME, it was on the far side. So it wasn't directed at us. In fact, we've had very, very little actually fire off that's between us. I'll just show you that again. So look for the big expulsion in the northwest quadrant, and then you'll literally see the snow hit us almost straight away. So here we go. Bang, there it goes. Oop, I've gone backwards, sorry. So let's go back forward. All right, okay then. No, I do want to go back. Excuse me. So now this is using the coronagraphs. Again, this is exactly the same object with the same event. So here we go. There's a one off to the south, and we get the big one off to the, there it goes, bang, and then all of a sudden we're hit with all this snow. And that's just highly energetic particles hitting the sensors in the actual observatory that's actually observing this at the moment. I think it's Soho, this one. I could be wrong. It could be SDO. But there we go. So here we go. I'll just run through these. Now, if you look at the orb, you see this is there's a big flare that happens on here, a big event. Now, this is the event I have said that happened on the just above over the side of the limb. And you can see we get a lot of reconnectivity going on, and you get this big loops coming up from the flare. I will start this one. So you'll see it a little bit closer. Bang, you see that? And then it ends up with all this reconnection. Now, there wasn't a CME connected with this, because when you look at the coronagraph, when this goes off, there is nothing ejected out into the thing. So let's have a look in this one. Down in the bottom left. You'll actually see some of the stuff, actually, there will be some lift off, but nothing. You can just see, it just shows you the arches in the actual magnetic arches that form between the sunspot regions, as I was saying. Now this one's a bit bright, so there we go on the pink. So there we go. It's just a little puff, but you can actually see again the reconnection going on and the arches forming from that one major event. And again, this was over an M class flare, but of course, not having anything to be able to measure it, we couldn't really measure the exact size of it. But it was just one of those things that happens. We have had things, and this is from that region that was circled. So if that carries on that way, then maybe we'll get some action. But other than that, this week we've had very, very little. Nothing's been directed our way. And this is just a close-up in the blue sun, which is 131, of that region at the time of the flare itself. And it was quite a bright event. And as I said, it's beyond the actual limb. Right, so what's coming? Well, as I said, it's all guesswork. We got no assets on the backside. These are regions that have been plotted using helioseismology rather than actual visible light, because we've had nothing to do with it. Remember, what's in the grey is what's on the sun's face at the moment, facing towards us. And this is the region that's coming. It was 3879 in old money. And very soon, this will possibly become 3910. There's another little dark region they're predicting, and here, but they can't see them, so they can't predict what's going on. If they are dark, that means that there's something possibly there that's well worth looking at. So what else we got? Oh, sorry. The only thing I've got to do is just go. For some unknown reason, I don't know why that. Just bear with me a second. No. Yeah, but basically, what we've got several regions now that have come up onto coming onto the sun's face now, which have mixed magnetic complexities, and they will possibly be giving us some fun and games over the next week or so. So that's it. I hope everybody enjoyed that. And just keep an eye on your alerts. There have been aurora, but they've all been up towards the north. It's sort of like around the Arctic Circle and probably just a little bit lower, but nothing that's going to affect us. So thank you very much.
Thank you, Daz. So there we are. So not a terribly active sun at the moment, but I'm sure that will change. There we are then. Just a reminder that we will not be on the air, so to speak, on Christmas Eve or on New Year's Eve. Just a word about something coming up in December that we've fixed a date for. On December the 17th, Tuesday, December the 17th, we've done a terrible thing. We've let Michael do a quiz.
Oh no!
We put it off, and we've just run out of excuses, Ian. And it's one of those things we have to grit and bear it. However, I'm sure Michael's, all joking aside, just for a change, I'm sure Michael's quiz will be enormously popular. So we did say we'd do another quiz before Christmas, so it's fixed for Tuesday, December the 17th. We hope you can join us for what should be, but probably won't, a wonderful evening. So there we are. So there we are. Okay, Michael, any preview of the quiz? What have we got to look forward to?
Oh, there's some space flight in it. There's photographs. There's name that galaxy, name that nebula, that sort of thing.
Ooh. Okay, can you send me a copy of the questions so I can scrutinize them and make sure?
You just want to get them, Peter.
Just the questions, and I can look up the answers myself before the day. So you carry on. Just want the questions.
On the other hand, Michael, can you send me a copy of the answers, please? I think.
Don't do the research, Andy. Don't do the research.
Well, listen.
If you have the answers, Andy, what will the question be?
Yes, indeed. Yeah. So anyway, we've got Michael's quiz to look forward to on the 13th of December. So with that, we would draw things to a close, for which you're probably quite grateful this evening, viewers. So thank you very much for being with us. Thank you for your contributions this evening. Much appreciated. We'll be back next week when Lou will be looking at the interesting subject of dark energy. So we got that to look forward to, and a few other things as well. So I'd like to wish you all a very, very happy and fulfilled and peaceful week. And so from all of us at Space Oddities, enjoy yourselves, look after each other, be good. If you can't be good, be average, as I always say. And we'll see you again next week. Thank you for being here. Much appreciated. So from all
Horlicks time. Horlicks.
Yes, absolutely. So